Greetings and welcome to my new calculus channel. My name is John Gabriel. So, I've been talking a lot about the subject of k divided by 1 equals to k and asking the question, is it always true in algebra? Well, the simple answer to that is no. It's not always true in algebra. In fact, in most cases, it's not true. But what is the reason behind that? Well, this video is dedicated to mainstream mathematics lecturers and teachers. It's a labor of love to re-educate them, get them out of their stupidity. So in just a few short pages, I'm going to show you how the brilliant ancient Greeks, parentheses, my ancestors, defined number in just a few pages using the most simple concepts, nothing like set theory or ZFC or all that nonsense, excuse me, that you find in mainstream mathematics. So we begin our lesson with a ratio of line segments, right? Let's make this bigger, easier to read. Oh, why isn't it getting bigger? There we go. Whoops, no, that didn't work. All right. So we don't have to use line segments. We can use any other type of magnitude, area, volume, whatever we like, mass, doesn't matter. But it's just that a line segment is the simplest magnitude, and it's the easiest to derive from nothing, without axioms or postulates or any of that gibberish, okay? Consider the ratio of magnitudes. Now, what are the magnitudes here? In this case, they're line segments, but I could have drawn areas or volumes or put something else on the antecedent and the consequent, or for the antecedent and the consequent. That's more correct English. So in geometry, we have no problem finding the measure of this ratio. How do we do that in geometry? Well, we take a divider like you see here. This little red instrument with a blue handle is a divider, used a lot in geometry and trigonometry. We place the ends on this side of the antecedent, and we say we only need that green part of the consequent to measure the antecedent, and we're done. It's as simple as that. Isn't that incredible? That's geometry, by the way. Now, in algebra, the process is not that simple. We need to find a common divisor, or, as the Greeks would rather say, a common measure. In other words, in Greek, kinometro. Okay, kinometro means common count or common measure. So, and by the way, the word measure appears in the elements hundreds of times. So that is, we need to find a line segment that fits exactly into both the antecedent, into both the antecedent, this part, and the consequent, this part, okay? It must fit exactly. There must be no remainder. It must measure it out without any remainder. So it turns out there is such a line segment, and it's this little guy here. Whoops, no, just the red one or the green one, okay? So this little line segment measures both the antecedent and the consequent. That's all we know right now. We don't even know how to count yet. So we'll call the measure of this ratio, the same little line segment to itself, a unit, okay? And the measures of multiples of the unit will form the counting numbers. So we'll say the measure of this ratio is 1, or 1 over 1, by the way. We write just 1 because we don't feel like writing 1 over 1. And here we write 2 because we're lazy. We don't write 2 over 1, 3, etc. So now we've got our counting numbers, and it should be a lot easier to measure the ratio mentioned early on. So here's the ratio that we had earlier on. Now we can count these. We can say 1, 2, 3, 4, and 1, 2, 3, right? So that means that 3 over 1 is the measure of the antecedent to the consequent, which is the unit magnitude, okay? And 4 over 1 is a measure of the consequent. Of the consequent to the unit magnitude. So that's the antecedent, and this is the consequent, okay? Always the one that appears before the colon is the antecedent, and the one after the consequent. I'm not too sure what the Greek words there are, but I think it's proegumeno and epakoulotho, which means before and the one that follows. So now, the measure of this ratio is very easy to find, isn't it? How do we measure it? It's simply the measure of 3/4, which we can write as 3/4. And now we have a number. 3/4 is a name we give to the measure of this ratio, okay? It's as simple as that. And as you can see, we realize numbers from ratios of magnitudes. And here's this beautiful definition, which the great John Gabriel gives to you. A number is a name given to a measure of a ratio of magnitudes. Simple as that. So you have no nonsense of set theory, ZFC axioms, any of that other mainstream drivel. But what if we had the following ratio? Now look at that ratio there. Isn't that interesting? This red antecedent part is a square diagonal, okay? And this blue consequent part is the side of the same square with this red diagonal, okay? So we know this is easy in geometry, but can we measure it in algebra? Think about that. Can we measure this in algebra? Is there a smaller line segment that measures this guy and this guy exactly without any remainder? Well, there is no such line segment. Oops. So that means this ratio here doesn't have a measure, okay? In other words, this ratio has no measure in algebra, and it can't be written as P over Q, because P over Q is the only kind of number you can have, okay? It's redundant to say rational number, because rational is an extra word. Number implies rationality, and rationality implies number. When you see square root 2, that's just a symbol for a constant. It's not a number, okay? It can be 1 or 1.4 or 1.41 or 1.414. Okay, I'm taking this slowly because math professors have a very limited attention span. So if you need to take a break now, go and get yourself some coffee or something. Stop the video and come back again. Okay, we're almost finished. Don't worry, we're almost finished. So square root 2 is not a measure of any kind, so it can't be called a number, okay? Right? You see? Did you see how I showed you here how you can actually measure a ratio starting right from the beginning? And then I presented this nasty little ratio here, which overwhelms your circuitry. Okay? Now, mainstream mathematics academics do not understand these things, but now hopefully with this video, they'll have a better chance. That's good coffee. Now, that's pretty much it. I am the great John Gabriel, discoverer of the new calculus. Follow me on academia.edu. There'll be a link in the description. Tell your friends about this. Become a subscriber. Click like. Spread the word so I can get 1 million subscribers and start earning something out of this and start getting some money so that I can live, so that I can rise out of my poverty, my self-induced poverty. Okay? Well, all you mathematics lecturers and teachers out there, don't say I don't love you because I did this for you. Okay, you're the main target of this. Most students in school and high school, they understand these things. They don't have a problem with this. The ones who have a problem are you, okay, with your PhDs and your BSs and all that garbage. So that's pretty much it. I'm John Gabriel. This is a new calculus channel. And until next time, goodbye, friends.